So we're going to continue working with our definition of entropy and look at different ways in which we can calculate the change in entropy of a chemical or physical process. We're also going to look at what's referred to as the third law of thermodynamics and just yet learn how we can use tabulated values in order to calculate some of these thermodynamic parameters. So just reviewing, the first law of thermodynamics, which is the law of conservation of energy, states that the change in energy of a system is equal and opposite to the change in energy of the surroundings. The second law of thermodynamics, which we were just introduced to, says that for any spontaneous process, the change in entropy of the universe is always a positive number. And we recognize that the change in entropy of the universe is equal to the sum of the change in entropy of our system plus the change in entropy of our surroundings. So what we can see is that the change in entropy of our system is always greater than the negative of the change in entropy of our surroundings. But it is important to realize that the change in entropy of our system is not equal to the negative of the change in energy of our surroundings. So it is different than what we see for the relationship with energy. Hopefully you can recognize that any process that leads to an increase in the number of microstates of the universe as a whole will have delta S greater than 0. So if we look at a system, we can kind of judge whether the microstates are increasing or decreasing by the disorder or randomness or flexibility of our system and decide whether we would expect that chemical or physical process would be delta S negative or delta S positive. So for example, there are instant cold packs that are based upon the dissolution of ammonium nitrate in water. And so let's think about what happens when ammonium nitrate, which is an ionic compound, it's a solid, is dissolved in water. Well, we know that this process is endothermic. It takes in heat because it makes the surroundings get cold. But we start with 1 mole of solid. We take in a bunch of heat which energizes the particles there and gives them some kinetic energy. And we end up with 2 moles of aqueous ions. So the particles that are on this side have more energy, and they also have a whole bunch more freedom of movement. We've also doubled the number of particles. So it makes it really clear that there's going to be a lot more microstates for the products than what there is for the reactants. So if I was looking at this, I would predict that delta S most definitely for this particular reaction would be positive. So in this case, delta S system is going to be positive. Now, if I was examining what was happening to the surroundings in this case, what would I decide about the entropy change of the surroundings? Well, I'm taking heat from the surroundings, so I'm kind of cooling everything down a bit, so stuff won't be able to move around as much. So I would predict that the microstates of the surroundings would decrease, and therefore delta S of surroundings would be a negative number. And that would be my kind of qualitative guess as to what is happening in this system. So one of the things that you'll have to do is look at a physical or chemical process and predict whether you would expect delta S for that system to be positive or negative, and then explain how you arrived at your answer. So in this case, we're taking liquid water, we're adding in some heat, and we're generating gaseous water. Now, I would predict that this will be a delta S positive process because the gaseous water is going to have a lot more freedom of motion than the liquid water. Additionally, we took in a bunch of energy, and that's just going to kind of make my my particles in my system have more kinetic energy, be moving around quicker. So I'm pretty confident that this is going to be a delta S positive process, and I could justify that. In this case, I'm reacting gaseous ammonia with gaseous hydrogen chloride to form ammonium chloride, which is identified as being a solid. So on the left, I've got 2 moles of gas, and gases we know have lots of freedom of movement. And then on the right here, I've got 1 mole of solid, where all of the particles are trapped in place in a crystal and are unable to move around a lot. So for that reason, I'm going to predict that this guy will be delta S negative. In this case, I'm taking a sugar. I can judge that this is a sugar because it looks like a carbohydrate. So carbohydrates have the formula where we have carbon combined with a multiple of hydrogen and oxygen in the ratio that is found in water. That's why they're called carbohydrates. So I can see that here, that A would be 12 and B looks like it's 11 there. So that's definitely a sugar of some description. It's solid. I'm dissolving it in water to generate an aqueous solution. So here, the number of particles isn't changing, but what's changing is I'm going from solid to aqueous, so these guys are going to have a lot more freedom. So for that reason, I'm going to predict that this process of dissolution would be delta S positive. So this is something that you're going to be asked to do, predict the sign of delta S for a particular system, and explain how you arrived at your prediction. Okay, we promised that we were going to talk about the third law of thermodynamics, and the third law of thermodynamics states that the entropy of a perfect crystal at 0 degrees Kelvin, that is when the system has no kinetic energy, is 0. So at 0 Kelvin, our system has no kinetic energy and all motion has ceased. For a perfect crystal, there's only one way of arranging the particles. There's no mistakes in our crystal. So therefore, that means that there is only one microstate. So according to Boltzmann's definition of the entropy, S is equal to K ln W, and ln of 1 is 0. So for a perfect crystal at 0 Kelvin, S equals 0. So we have a 0 on our entropy scale, and we can measure everything relative to that. Okay, so every other substance can be placed on our entropy scale relative to this 0 point. So this allows us to define the absolute entropy value relative to the 0 point for a particular substance. And for a particular substance, this is reported as the standard molar entropy. So this is the entropy of 1 mole of a substance at standard conditions. And standard conditions are a temperature of 298 K, a pressure of 1 bar, and the substance is in its standard state. And standard state means if it's a solid, it's the pure solid. If it's a liquid, it's the pure liquid. If it's a solution, it means that the concentration equals 1 molar. And if it's a gas, it means the pressure is 1 atm. There are some other things as well. If we have sort of like multiple elemental forms of a particular kind of atom, then we're going to go with the most common one. And where this comes into play in particular is when we're talking about the standard state of carbon, we mean for carbon in the graphite form, not the diamond form. So there's a whole bunch of these standard molar entropies listed in the appendix of your book. It's not appendix 4 anymore. I think it might be appendix G. So here are some standard molar entropies of a range of substances, and you notice some obvious trends. The standard molar entropy of gases are always greater than the standard molar entropies of the corresponding liquid. And often there's a very big difference. So here we've got liquid bromine versus gaseous bromine. You can see the gas has a much bigger standard molar entropy. Liquid water versus gaseous water, and again the gaseous form much bigger entropy. And all the way through here, liquid methanol versus gaseous methanol, the gaseous has a much bigger standard molar entropy. This is ethanol. So in here, ethanol, there we go. So we've got liquid ethanol versus gaseous ethanol. Gaseous is a lot bigger. And then in here we've got propane. So for some reason this box has kind of moved. So where have we got propane in here? No, we've only got gaseous propane. Let's have a look in here. We've got butane. So liquid butane versus gaseous butane. And the gaseous form has a bigger standard molar entropy. And then we've got benzene, liquid versus gaseous. And again, the gaseous form has a bigger standard molar entropy. That's not that surprising, right? Gases have much greater freedom of movement than liquids. So as a general rule, as we go from solid to liquid to gas, the standard molar entropy increases. And we do see a really big increase in the standard molar entropy when we go from liquid to gas, because, you know, gases have a lot of freedom of movement. They have infinite volume, effectively. They could occupy the whole atmosphere if we allowed them to. So you always get a big entropy change when you go from one state to another. Okay, the other thing that we'll observe is that as we increase the molar mass or the molecular size of a molecule, the standard molar entropy increases. So here are a series of what we call hydrocarbons, and you can see that as we increase the number of atoms that's present in the molecule, that the standard molar entropy increases. Now, why is this? Well, it's pretty simple. That the larger the molecule is, the greater variety of vibrations, rotations, and translations that are possible, i.e. there are more microstates. And how do we define entropy? It's just k times by the natural logarithm of the number of microstates. So as W goes up, the standard molar entropy goes up. The standard molar entropy is also going to be influenced by the rigidity or the flexibility of a substance. So here's diamond, where we have sp3 hybridized carbon atoms. Every carbon atom is connected to 4 others in a tetrahedral arrangement. It forms a covalent network solid. It's extremely rigid, and it has a a fairly low standard molar entropy. If we go to graphite, where we have layers of carbon atoms, every carbon atom is sp2 hybridized and bonded to 3 others in a trigonal planar arrangement, we have only weak dispersion forces between the layers. There's a lot more flexibility in this structure. This structure, the atoms are able to move around more. Those layers can slide because we have weak, what we call pi bonds between the layers. We have weak dispersion forces between the layers. These are referred to as pi bonds sometimes. So the layers easily slide past one another, and we have a relatively high standard molar entropy. So things that tend to increase the entropy of your system: increased temperature. Your particles just have more kinetic energy. They're moving around more. They can rotate in more different ways. They can vibrate in more different ways. They can translate in a greater variety of ways. Increased volume. They have more space to move in. The ways that they can translate is increased. Increased number of particles. When you go from a few particles to many particles, you have a greater number of microstates. You are increasing the entropy of your system. And increased particle freedom of motion. So rigid systems have lower entropy than more flexible, more wobbly systems, if you will. Okay, so if you're given a balanced equation, you should be able to qualitatively predict whether that chemical or physical process would be expected to have delta S that was positive or delta S that was negative. And you should also be able to explain your answer. So we've talked about this previously as well. So here's a system here. On the left here, it looks like, it's combustion of a hydrocarbon. So I'm reacting some propane with some oxygen. And on the left here, I've got 6 moles of gas. And I'm looking at this and I'm thinking that's a pretty big flexible molecule. It's probably got like a significant standard molar entropy. Over on the right-hand side here, I've got 3 plus 4. I've got 7 moles of gas. Okay, and each of these molecules have 3 atoms in them. Okay. So now I'm kind of like, making some decisions here. It says it's constant pressure. Okay, so that must mean that the container, the volume goes up. And I know the volume goes up is because if for it to be at constant pressure as I make gas, if the volume didn't go up, the pressure would go up. It's at constant temperature. Okay, so that's not going to make any difference to things. I'm not going to kind of like increase nor decrease the the total energy of my system. All right, so what I'm going to decide is that this is going to be delta S positive. And my reasoning is that I've got more moles of gas. And because the pressure is constant, then the volume of my system has to increase. And both of those things are going to lead to an increase in entropy, right? So that's an example of how I might tackle one of these problems. So let's have a look at another couple of examples. So these are at constant pressure and temperature. Okay, so what's happened here? I've got a solid reacting with an aqueous solution, and I've got 3 moles of stuff total. And then over here, I've got 3 moles of stuff total, but what's cool is I got 1 mole of gas, I got 1 mole of liquid, and I've got, this is an aqueous solution of an ionic compound that's going to separate out into ions. So this actually is like 3 moles of ions in here. So I don't have 3 moles of stuff really, I really have 5 moles of stuff. And in addition, I've gone from having like a mole of solid to having 3 moles of these ions that are in aqueous solution. I've also created a mole of gas. Oh my gosh, this, so much more microstates on the right hand side. This has to be delta S positive. Alright, now if I look at the next one, what have I got? Well, on the left here, I got 2 moles of gas. And on the right here, I got 1 mole of solid. Oh, well, this is definitely going to be delta S negative. I've reduced my total number of moles of particles, and I've also trapped everything in the solid where it has very little freedom of movement. So that's the kind of thing that you should be able to do. Now, it also turns out that if you're given these standard molar entropy values, you can actually quantitatively calculate a standard molar entropy change for your physical or chemical process. And it's very similar to what we were doing with enthalpy. What you do is to get the entropy change for your reaction is you add together all of the standard molar entropies of your products, and then you subtract from that the sum of all of your standard molar entropies of your surroundings. And by delta S reaction here, we mean delta S system. So there are these tables in the back of the book. We can use the values that are in the tables to do this math, and we can calculate delta S for our system. Now that's kind of fun and all, but we know that to predict spontaneity, we need to calculate delta S of the universe, and if that number is greater than 0, then it will be spontaneous. And so far, we've learned how to calculate delta S of the system. How do we calculate delta S of the surroundings? Well, we learned earlier that for a reaction occurring at constant pressure and temperature, the enthalpy of the reaction will be equal to the heat transferred to the system or from the surroundings. So we can put this into our relationship for delta S, and we said earlier that the delta S of the surroundings was equal to the heat transferred to or from the surroundings divided by the temperature of the surroundings. And if I look up here, I can see that the heat transferred to or from the surroundings is just going to be equal to the negative of the enthalpy of our reaction. We also know, and I mentioned this just a moment ago, that we can do a Hess's law type calculation to use tabulated values of the heat of formations of our reactants and products to calculate the enthalpy change of a reaction. And to do that, we just add together all of the enthalpies of formation of our products and then subtract from that the enthalpy of formations of our reactants. So what this means is we can do two Hess's law type calculations to calculate the entropy change of our surroundings and the entropy change of our system, and then add those numbers together and get the entropy change of the universe and predict spontaneity. So let's do an example because it's kind of, long-winded this, right? So we're going to form ammonia from its elements at 298 K and 1 bar. So really what this is saying is that everything is going to be at standard conditions, which we indicate with the $sign. So we're going to need a balanced reaction, and here it is. Okay. So hydrogen and nitrogen reacting to form gaseous ammonia at standard conditions. The first thing we're asked to do is to predict the sign of the entropy change accompanying this reaction. Now, considering that I've got 4 moles of gas on the left and only 2 moles of gas on the right, I'm predicting that this reaction will have a negative entropy change. So I can now go ahead and calculate the entropy change for this system using standard molar entropies. So and take the standard molar entropies of my products, add all of those together, and subtract from that the sum of the standard molar entropies of my reactants. So I've got 2 ammonias, and they each have a standard molar entropy of 192.5 joules per Kelvin, and then I'm going to subtract from that 3 times the standard molar entropy of H2 plus 1 times the standard molar entropy of N2, and then that gives me an entropy change for this reaction of minus 198.3 joules per Kelvin, which I'm happy with because it's in agreement with my estimate that I got, or with at least the sign that I estimated for 4 moles of gas going to 2 moles of gas. So that's happy. I'm happy there. Now what I'm going to do is, I've done this bit now, I've done that bit, is go ahead and calculate delta S for the surroundings. So remember how we're going to do this is via the enthalpy. So to get delta S of the surroundings, the little formula that we're going to use is it is the negative of the enthalpy change of the reaction divided by the temperature of the surroundings. The temperature of the surroundings is 298 Kelvin, so I've got that there. And how I'm going to get the enthalpy change how I'm going to get the enthalpy change is by doing a Hess's law type calculation. So I need to sum together the enthalpies of formation of our products, which was our ammonia, and then subtract from that the sum of the enthalpy of formations of our reactants, which was our hydrogen and our nitrogen. So don't forget the minus sign. There it is right out the front there. So I've got 2 times the enthalpy of formation of our ammonia minus, so I should just write that out, what the reaction is. There we go, just so we can keep track of everything. Minus 3 times the enthalpy of formation of hydrogen, which is 0, plus 1 times the enthalpy of formation of nitrogen. So when I do all of this, I do have to take into account that the values for the enthalpies of formation are given in kilojoules per mole. I need to turn those into joules per mole or I'm going to have trouble later on. And so I've done that here. I just added on the times 10 to the 3 to the value to get that. So I do the math and I end up with the delta S of the surroundings being 309.4 joules per mole per degree Kelvin. So now I'm going to just add these guys together, the delta S of the surroundings, which I just calculated, plus delta S of the system, which I calculated in the previous section, part 2 of the problem. Add these 2 guys together gives me delta S of the universe. So if this, and this is why you have to make sure that they have the same units, so which they do. And then now what do I get? I get a positive number, right? So delta S of the universe is positive. So what does that mean with respect to spontaneity? It means that this process will be spontaneous, right? Has to be spontaneous if delta S universe is positive. Okay, so sort of slightly long-winded, but we got there. If you could have an attempt at these 3 problems before the Wednesday Zoom session when I'll be going through them, that would be very helpful.